I'm going to talk about our recent work on detecting violations of differential privacy. This work is done in collaboration with Zeyu Ding and Guanhong Wang, and is supervised by Dr. Danfeng Zhang and Dr. Daniel Kiefer. The previous talk has talked much about the differential privacy, so here I will not repeat and address the importance and the benefits we can get from satisfying differential privacy and dive into the motivation of our work. Since Cynthia DeWart gave a formal mathematical definition of differential privacy, we have seen a lot of publications about new algorithms in many areas claiming they satisfy differential privacy. However, it is hard to design and prove the algorithms, and many algorithms turn out to be incorrect. Then an interesting and important question arises. How can we detect if the algorithm is incorrect in the development process so that programmers will be able to know that their algorithms are likely not to satisfy differential privacy? Also, how can we provide hints to the programmers to fix their code in an early stage? Our goal is to build a tool to test the designs of the algorithm and report counterexamples to the programmer if the algorithm fails the test. In that way, the programmer will be able to fix the bugs in an early stage before releasing their algorithms to the public. Our tool is designed to run in a semi-black box manner. That is, we execute a code with a variety of inputs and analyze the output without concerning the actual implementations. So we'll have no restrictions on the noise mechanisms being used, and we will have no restrictions on the programming languages you're using. Sometimes, if the algorithm needs additional arguments to run, we'll have to know the source code and run some tests on it, and I will cover this later. We use pure differential privacy definition in our work. An algorithm is set to satisfy differential privacy if the probabilities of seeing any output from running on adjacent databases are bounded by some constant. Note that here we use E as an event to represent the output space. As I've said, our tool is able to provide counterexamples when an algorithm fails our test. A very important question must first be answered. What consists of a good counterexample? We define a counterexample of our tool by two components. The first one is a pair of adjacent databases, as in the definition of differential privacy. 2, an event of possible outputs of the algorithm. A counterexample is valid such that there exists strong evidence that differential privacy is violated. That is, the formal formula doesn't hold with this particular counterexample. Now I'll give you an overview of our tool, how our tool is able to detect counterexamples. First, we find candidate databases D1 and D2 in a small but highly representative set. We call this input generation. Second, for every database candidate, we find a suitable E event. To do this, we run hypothesis tests in exploratory mode to find the best one in a confined search space. I will cover the hypothesis testing later in this talk. Third, for every database and event tuple, we run a hypothesis test to try to generate evidence that this tuple violates differential privacy, which makes it a valid counterexample. And now I will elaborate each component of our tool in a reverse order, starting from the core of our tool. Now let us assume that we have found a counterexample candidate. How can we show that there is a strong evidence that this particular counterexample violates differential privacy? The answer is we use hypothesis testing to accomplish this task. In the rest of the talk, I'll use P1 to indicate the probability of seeing E by running the algorithm with D1, and P2 by running the algorithm with D2. The hypothesis test works in this way. Suppose P1 is less or equal than E to the epsilon times P2. That is, we suppose this counterexample satisfies the differential privacy. This assumption is called null hypothesis, and the probability of seeing a data sample under the null hypothesis is bounded by so-called p-value. If the p-value is small enough, we consider it as a strong evidence that the null hypothesis is not true. Thus, this tuple is a valid counterexample. The problem is then divided into two parts. The first one is how can we get a data sample, and the second one is how can we calculate the p-values based on the data samples. Getting the data samples is easy. We obtain data samples from running the algorithm with D1 for many times. We count how many outputs are in event E. We denote this number as C1. Then we do the same process for D2 to get a corresponding number C2. Note that the C1 is equivalent from the binomial distribution with parameters n and p1. In this way, we can get enough data samples to test our assumptions. Then how can we calculate p-values? The difficulty is that we don't know p1 and p2, and it's hard to estimate them. But we only care about if p1 and p2 satisfy the formula or not. And Fisher's exact test is a well-known method to compare two binomial distribution. It's based on the fact that when p1 equals p2, the joint distribution of c1 and c2 is hypergeometric. Therefore, even if we don't know p1 and p2, we can compute the exact p-value based on c1 and c2 and n. Here, we can downsample a c1 tilde from a binomial distribution with parameters c1 and 1 over e to the epsilon, and apply Fisher's exact test to calculate the p-value. Now we can generate evidence to test if a counterexample is indeed valid or not. I'll move on to the next component of our tool, event selection. In the hypothesis test, we assume we have already found a counterexample, which is a tuple of adjacent databases D1, D2, and event E. The next question is, given an adjacent database pair D1 and D2, how can we find a good event E where differential privacy is indeed violated? From the graph, we can see the better E could be in the middle bar since the probability under two databases are more differentiated. To do this, we run a hypothesis test in exploratory mode on a confined search space. That is, we adopt the same method of running hypothesis test but sampling less from the algorithms for better performance, and choose the event with the smallest p-value as the best candidate. Since the event is related to the algorithm's output, we have different strategies to choose the search space for events. For example, if the output of the algorithm is a list of booleans, we could just let E be the set of output with 5 truths. Or if the algorithm returns a list of reals, we can let E be the set of output with minimal value in the range from -1 to +1. The last question to be answered is how we can find good database candidates D1 and D2. The goal of our tool is to provide simple and human-understandable counterexamples for programmers. So we confine the search space to a small set, and we do exhaustive search. Pairs in this set should be representative. That is, they should have the maximum differences. In this way, it is more likely to detect counterexamples and provide better useful hints at the same time. Following this rule, we have picked some representative categories of database pairs, such as one above and rest below, where only one element differs from the other databases by +1, and the rest differs by -1. And half-half, where half of the elements differs by -1 and the other half differs by +1. We found this simple and generic approach works surprisingly well. For some other algorithms that need additional arguments, such as the sparse vector technique, this algorithm tests if the query is above the preset threshold t and output true if yes. The number of truths it can output is bounded by the argument m. In this algorithm, t and n are needed for us to run the algorithm. So to find suitable additional arguments, we adopt state-of-the-art symbolic execution with 2 heuristics. If the arguments affect noise generation, we try to minimize the noise, since less noise yields more accurate outputs and a likely better differentiation of D1 and D2. If not, we try to maximum the number of divergent branches, since divergent branches will likely use more privacy budget. With this, we can get answers from the symbolic execution about the possible values of the additional arguments. We then provide these arguments along with the database pairs. To show the power of our tool, I'll demonstrate some of the evaluations we have done in our paper. If the algorithm M claims to be epsilon0 differentially private, we run our tool for a range of epsilons containing epsilon0. We then plot the p-values of the counterexample found for every epsilon. As I have elaborated, if the p-value being close to 0, it means we have a strong evidence that M is not epsilon 0 differentially private. And these are 3 sample plots we have generated. The x-axis represents the test epsilons we have used, and the y-axis is the p-value. The algorithm we used claims it satisfies 0.7 differential privacy. Thus, if the plot looks like the first one, the p-value remains close to 0 before 0.6 and rises to 1 after 0.7. It shows that M correctly claims it satisfies 0.7 differential privacy. If the plot looks like a second one, the p-values rise earlier than 0.7. It means M could indeed satisfy 0.5 differential privacy, and the authors could be too conservative about their algorithms. The most interesting case is the third one. The p-values do not rise until around 1.5. It means we have found a valid counterexample to show that the algorithm M may indeed satisfy 1.5 differential privacy instead of the claimed 0.7. For a specific case, the sparse vector technique, the blue one represents the experiment we set. In this experiment, we set the algorithm's privacy budget to 0.2. It is equivalent to an algorithm claiming it satisfies 0.2 differential privacy. And the orange one is when we set it to be 0.7, and the green one is for algorithm epsilon equals to 1.5. Our tool shows that no violations are found for the correct implementations, as the p-value arises at their expected value. For one incorrect implementation of the sparse vector technique, our tool shows that counterexamples are valid. Moreover, our tool provides good estimates for the actual privacy bound of this algorithm. We conducted our evaluations on multiple algorithms and their incorrect variants and found no violations on the correct implementations. For all incorrect variants, our tool is able to give a human understandable counterexample for programmer to fix their code. The average time spent on running one detection is within 23 seconds, showing that our tool is fast enough to be used in the development process, and our tool is publicly available on GitHub. That concludes my talk. Thank you. Yes, please.
So I have a question. So suppose that somebody designed a mechanism and he didn't care about differential privacy, but then later he wants to use your technique to know if his mechanism is differentially private for some epsilon. Can you use it to be able to find this? I mean.
Yes, correct. Because the algorithms we studied they take a privacy budget epsilon as their argument. So if you doesn't care about differential privacy, you wouldn't use a privacy budget in the first place. But you can just run our tool with your algorithms, and you can set a test epsilon. Because if you're interested, if your algorithm satisfies 0.5 differential privacy, you can just use 0.5. As the test epsilon to test if your algorithm satisfies or not.
Okay, thank you.
Hello.
Hi.
So your exploratory mode finds a whole bunch of events and inputs that you want to test in
Correct.
your second one.
Correct.
But your second stage is testing a whole bunch of them, so it's like multiple hypothesis testing.
Yes.
Which typically requires some sort of correction, but I didn't see you mention any correction.
What do you mean by corrections?
When you test multiple hypotheses, you might end up getting p-values that look significant just because you're testing so many of them by random chance. So if you look at enough inputs and events, eventually you're going to get one that looks suspicious just by being unlucky, for example, in your case.
Yeah, if we average the results to reduce the variance.
Okay.
If we average the p-values to reduce the variance, in case that one particular sample looks suspicious.
So then what are you going to do if the algorithm only fails on one set of inputs?
We have run multiple tests, and we do an average on that p-values. So if the p-value is really close to 0, it means that we have a strong evidence.
Okay.
You said that in some cases you realize that the algorithm is actually more private than it claims to be. How often does this happen in practice? And also, does this happen because you're just not checking on the right inputs? You're not just considering the actual worst case of the algorithm? And how much is that actually like the algorithm is more differentially private than it claims?
Okay, one thing I have to clarify is that it could be more differentially private, because when the p-value becomes that rises to 1, it shows that R2 is not able to provide a strong evidence that it doesn't satisfy differential privacy. But it doesn't mean that it's indeed 0. Just like the example I have shown, that it is indeed 0.5 differential privacy. It just shows that if you test epsilon is set to 0.5, we can provide counterexample.
Right. My question that how often does that happen in practice? Like in practice, if you run this and you don't find a good example, like does this really mean that there is none, or does this really mean that you just didn't find it?
From our experiments, that it happened very, very rarely. But for practical algorithms, I don't know that answer.
So we know that there's this whole family of attacks for differential privacy based on problems with floating point. So I was wondering if your method could actually find violations coming from problems with floating points.
Can you repeat the floating point?
Yeah, so like people have shown, for example, Ilya Mironov had a paper a while back, and he showed that if you have something that is differentially private, epsilon differentially private, but under the reals, and you implement it in a floating point computer, then it is not differentially private anymore. Yeah. And I was wondering if you can find these sort of violations.
Our assumption is that all the numbers are in reals, all the numbers are rational numbers instead of the floating point.
I have a question about neighboring relations. Can you support more than Hamilton distance? And if so, how far can you go? I guess you can't support arbitrary relations, right?
How far? You mean Hamming distances?
Hamming distance, thanks. Can you do more than Hamming distance?
Yes. Actually, if you refer to our paper, we have a lot of categories to choose from.
Exactly. What's the border? Where does it stop? What kind of neighboring relations can you not express?
What kind of... I'm not sure what you are...
Okay. We can take this offline.
Yeah, we can take this offline.
A follow-up on Borja's question. What do you mean by all of the really considered are considered rational? Like, how does it work with like Laplace noise? Laplace noise doesn't give you rational numbers, right?
Yes.
But you said that you were only considering rational numbers for some reason, which I don't understand what you meant.
We have the assumption that the numbers are rationals.
But that is a... Wait, what is rational? Because like the output of a Laplace mechanism is like not rational. So if you're assuming that's rational and you base your analysis on this...
I'm not saying the R2 is not suitable for the floating point, the problem he mentioned.
Okay.
So since there is time, maybe I have one question there. I mean, actually, the formulation of differential privacy which you're using is actually saying you're quantifying over all possible subset of the output space. But when you're in the epsilon 0 case, it actually suffices to consider singleton points. So instead of looking for a subset, you could be looking for a single element, and this is not what you are doing. So have you thought a bit about the trade-off of trying to find a subset versus trying to find a single point for violation?
It could happen that a singleton, the probability of seeing a singleton is very rare. And if you are using a subset, it could be the probability could be more. And if the probability is really small, it's really hard to detect a counterexample.
So it's better to deal with subset as you do. This is what you're saying.
Yes.
Okay. And since there is still a bit of time, maybe I could use a general question. You didn't speak too much about a verification-based approach to differential privacy, which are achieving more and more automation. So maybe you can actually say a few words about how you see that this complements your own work. Or
this is like another approach to tackle this problem. Verification is one space, and our tool it's like doing them in a reverse order to tackle this problem. And verification provides guarantees that a program is satisfied differential privacy, but it doesn't provide counterexamples if it's not. So this could be a very complement to this problem.
Okay. And since we have 2 minutes left, do you want to comment on the last paper of the session?
Yeah, the last paper, I think they use confidence intervals, and instead we use hypothesis test, and to do the job. And they use some kind of a solver to guarantee that there's a counterexample is really a valid counterexample. And actually, I think if our tool found a counterexample, we can use the same solver to make sure that this counterexample is indeed valid.
Okay, so thanks a lot. Oh, sorry. Yeah, I'm sorry.
Thank you. So if I understand correctly, your method is trying to optimize the space in some sense of finding violation.
Yes.
And I figure it's possible that there is a violation, but you actually don't find because of the error, etc.
Because the p-value is too large.
Right. So from your experience, how often does that happen at all? Or like vice versa, if there's no violation, can you maybe make a mistake and think that there might be?
Actually, this error rate is bounded by the p-values, so-called p-values. So if the p-value is small, then we can show that the counterexample is valid. But if the p-value is high, actually we can provide no answers to that.
No, I think I was wondering more on the sort of this previous step before the p-value, when you do like some sampling, etc. Could it be possible that there's some error associated with those process that could propagate to your estimation or whatever?
Before the hypothesis, before we calculate the p-values, we don't know a counterexample is valid or not.
Oh, yes. Thank you.
Thanks a lot.